Oh, we just started recording. Okay. Well, I'll end the introduction.
Sorry, Jason. Are you okay?
No, it's fine.
Yeah. Okay.
That's fine. So for people who are just joining us now, welcome. So what I want to say is, from this point of view, how do we introduce various machine learning concepts? So let's move over here, get some white space. All right. So here's the machine learning concept. And over here we have the linguistic or computational linguistic correlate. So the first thing that machine learning people do is they learn tasks. They set up tasks. And so what are tasks for us? Well, there's things that people can do with language. So that's competence. We're able to, somebody gives us a sentence and we're able to diagram it. We're able to respond to it. They give us a word and we're in English and we're allowed to convert it to Pig Latin, even though nobody told us about the distinction between consonants and vowels or syllable structure. So the next thing we learn about in machine learning is that there's models. So why do we have to teach about models? Well, this is a kind of fairy tale about performance. So it's what humans pay attention to. And then we have the notion of learning. So this might be parameter tuning if we're doing learning in a continuous space. And so this is, maybe human learning. It's at least a fairy tale again about how humans might learn, but there's a caution. This is very different data. So most of the time when we train systems, we train them on the data that we actually have, rather than the kinds of interactions that you and I had when we were learning our native languages. So the next thing we might have to teach them about in a general ML course is hyperparameter tuning in order to get the learning to work. Sorry about my handwriting here. I'm trying to write fast. And so this might correspond to what? Maybe evolution, where we want to get a learning algorithm that actually works on the kind of data we're actually going to see. And the hyperparameters are going to be evaluated somehow, and we have to teach them about evaluation in an ML course. And this is all like, in the setting of once you've set your task, how do you solve it? So this is about generalization, whether we actually manage to generalize onto a test set. And we're interested in the generalization capacity of our model. And this leads us to talk about some things like variance. So what does it mean to achieve, so we're gonna have bias and variance. What does it mean to have small variance? So this is something that I thought when I was taking my first linguistics course was just super amazing. Low variance means that we all see different, we're all exposed to different data. So I'm a native speaker of English. If you're also a native speaker of English, you heard totally different sentences than I did when you were growing up. And yet we still agree that some sentences of the language are okay and some of them sound funny. And for the ones that are okay, we agree on what they probably mean. So this is different humans agree. That's what it means to have low variance. And what does it mean to have maybe we don't have low bias, but we have a particular inductive bias. So why do we have that bias? What kinds of things are we drawn toward looking at? So here you should think about universal grammar, or the way we might think about it nowadays is that there's some universal prior. So you're looking for something which has high likelihood after you've looked at the data, but should also have a high prior. It looks like a reasonable human language. And so now this is a vehicle for teaching people about Bayesian machine learning, but in a particular setting of language. We have to convince them that this is interesting by telling them stories about inductive bias of humans, like the way that Creoles have things in common, or sign languages that evolve out of that children acquire from their non-signing parents, non-natively signing parents, tend to be different from what their parents are giving them, which reflects some notion of what seems to be natural in a language. There's another case, reason that bias shows up, which is smoothing. So even though you may never have seen something, you generalize to it, and of all the things that you've never seen, you think that all of them are possible, maybe, and some of them are more probable than others. So this is closely related, but it's basically how we discover that there's a universal prior as we take cases that there was some inductive bias, is we look at what you believe about things that you've rarely seen or never seen. Okay, so all of this sort of motivates Bayes' theorem, maybe, which any good machine learning course should have. And when we look at Bayes' theorem, the main reason that this comes in, the first place we'll put it in is not for Bayes' theorem for learning, where you're trying to find parameters you're trying to find a posterior distribution over parameters. Bayes' theorem comes in first for reasoning. So if you have some generative model, maybe a noisy channel, you want to be able to do inference. And we need fancy algorithms for this when the reasoning is structured. So you say something like, I know that the human generated a tree, because that's what they do. They generate trees. And now I see some sequence of words here at the bottom. And given the red stuff, I want to infer the black stuff. So there's a prior, which is given by a PCFG or something. And I have an observation, which is a string of words, or maybe just a speech signal, which is noisily, or text with typos or something, which is noisily derived from that string of words. And I want to reconstruct the black stuff from the red stuff so that it's a good explanation of the red stuff. So we're just going to maximize find the posterior distribution over trees, and either maximize over that or sample it. So all of these things that people teach in general ways in machine learning, I'm just much happier teaching them in sort of this grounded setting where we have this set of related problems that we've motivated up front from some overall goal. And I'll talk a little later about some other kinds of goals that we might have. So the next thing that shows up as our models get fancier is that we end up with approximation algorithms. So maybe we can do dynamic programming here if we have something like a PCFG, but more generally, we might have approximation algorithms, by which I would include all kinds of stuff, fancy approximation algorithms like variational methods and Gibbs sampling and particle filtering and beam search and stuff like that, but even also simpler things like pipelines and other hackery, where you snap together different Legos and try to get out some answer. And what this corresponds to in the human side we're trying to model what humans do is what psychologists and behavioral economists call bounded rationality. So people don't always get the right answer. And it's interesting to ask the question about whether our models of, when I say model, I don't mean now a probabilistic model. I mean the approximation algorithm as a model of human cognition, whether that's a good model and predicts the kinds of errors that people make and the reaction times and so on. And so I actually like to throw in a lecture on psycholinguistics just to raise this question where we talk about things like eye tracking experiments. So now the next thing that tends to show up after we've set all this up is we're interested in non-generative approaches. So we don't have a full generative model. So this is end-to-end or other simpler discriminative approaches. And so why would we talk about this? So this is, if we go back to cognitive science, Daniel Kahneman likes to talk about system 1 versus system 2. So system 2 is where you have a full model and you can do some kind of reasoning as we were doing above. System 1 is where you just have a policy. So you're just learning how to act and you skip over trying to figure out how the world works. And we see this in reinforcement learning, for example, where you can try to learn how the environment behaves and then reason by planning about what you should do as a result. Or you could just learn a policy directly that tends to work well for your given reward structure, but if the rewards change, then you're out of luck. So models are good for learning across tasks. Policies are good for being able to fine tune on a particular task. And the relation between these has been of interest, I think, for a long time. There are various reasons that we have gone to discriminative methods. Sometimes inference is easier, but that's also effectively why people do it in things like reinforcement learning, and it's why organisms may do it. So Peter Dion, for example, has studied a lot whether the transition from system 2 to system 1 in, for example, mice running mazes as they kind of compile their knowledge of the model into habits. Okay, so all of these models that we're building, we tend to have features or covariates. And so what do these correspond to over here on the linguistic or cognitive science side? This is what humans pay attention to. So an example would be violable constraints in optimality theory, or latent trees, and features. Sorry, I should say, when I say feature here, I mean, let's call these attributes. So we have morphological and phonological attributes. I want to distinguish those from features in the sense of things that have weights on them. So these are things that linguists care about. And I still like to go through a phase in my class where I talk about hand-done feature engineering, where you might want to build some inductive bias into your model, knowing something as a linguist. And then when we have latent, I'm sorry, when we try to learn our features because it turned out to be too hard to engineer them, and so learning embeddings and learning, let's just call it deep learning. So this basically corresponds to representation learning. So this is discovering features. This was, in the early days of multi-layer perceptron. This is discovering features through experience. Sorry about the handwriting. In the early days of perceptrons, the idea is you put in a bunch of features, and then you had this linear classifier, and the question is where the features came from. And an early name for these features here, when you added another layer, was adaptive basis functions. So you were going to re-express your input in some non-linearly transformed way, which was choosing a kind of new basis through which you could see the input. And so learning these representations goes back to maybe even as early as the original perceptrons paper in 1957, but at least the 60s. So once we're embedding stuff, and especially once we're embedding things that are more than just words, these are the learned representations, and these end up taking the place. These end up taking the place of things like lambda terms, where we had hand-engineered representation. And this is actually how I teach embedding now. So I get all the way up through semantics, and I'm teaching people. So we built these trees. So here basically is the syllabus of my class. We start by saying language is super complicated. Language is super complicated. And if you don't believe me, try to write a grammar. So the students struggle to try to write some reasonable grammar, and they generate random text from it, or they run their own text through a parser, so they can see both precision to see whether they're generating good stuff or crap as well as recall, whether the stuff that they want to put in can actually be parsed under their grammar. So language is super complicated. So they've got trees up front. And then later on, after we've learned probabilities and we've learned how to, so we do n-gram models, and eventually we get we get up to the point where we can do things like learn PCFGs and do parsing. And now the question is, what were these trees for? Well, we've got a tree because following like Montague, and I'm showing my age here, although I wasn't around in Montague's time, this stuff was still, what we learned in linguistics classes when I was a CS grad student. So we have here again these words, and these words have meanings, and we can build up meanings of the phrases, and we have this recursive thing. And as we try to figure out what the lambda terms end up looking like here, we get these horrible things with nested parentheses, and there are a lot of things that we have to admit that we can't engineer all that well. And so the question is, could we do the same thing? Could we simplify a way where we're doing the same thing, where we just, all these red things, instead of being lambda terms, turn into green things, which are embeddings. And so we could build an embedding of a structured object from the embeddings of its subobjects. And we can do that all the way down. And now we have recursive encoding of a tree. And again, this is meant to give them the sense that, yeah, you can really encode anything. You can do anything you want. Given an object, you can turn it into given a data structure, you can turn it into embedding. And these now become the universal solvent, which allow you to snap together different kinds of data structures where you might want to have a task that encodes one and decodes into another, for example. So at this point, we can go into a lot of encoders and decoders with some sense of what it is, with some sense of what it is that we might want to encode and decode, and use this very generic method for encoding data structures that we've been experiencing already in the first half of the class. And by the way, when you want to build a sequence, so we've got a bunch of words here. So when you have an RNN, that's exactly encoding a tree. It's just encoding, happens to be a right branching tree. So the hidden state at every time step is obtained, from the current word together with the hidden state at the previous time step. So that's basically an RNN. So we kind of built up all the way through the classic stuff, and then we started taking it apart again, where we said, did we actually need trees in order to build this, or could the states that we're encoding actually replace this stuff? So let me finish this up here, and then I'm going to sketch a few other ways that we could just finish up this correspondence between machine learning and computational linguistics, and then I'll unpack a little more of what this kind of historical view looks like. So once we are doing, once we say maybe we can simplify by just getting rid of the trees and making everything right branching, or sorry, left branching in this case, now this starts to look like, what is it that the hidden state after we see the first four words has to tell us? So what the hidden state tells us is maybe not a single tree, but maybe a mixture over lots of different trees. So as we go left to right, we need some way of encoding the first four words, which is compatible with all the things that might have happened next. And in my class, at least, I know this is a little out of fashion, we have already done Early's algorithm, which is also a way of saying after you've seen four words, you have a sense of all the things that might happen next. Early's algorithm can give you a probabilistic prediction of all of the next possible words. And so this lets me make the point that these embeddings are really capturing all kinds of information, including some distribution over syntactic possibilities rather than committing to just one. And that's the same thing that we have in HMMs, where when you have, say, an alpha vector in an HMM, it'd say, well, we could be in state 1, or we could be in state 2, or we could be in state 3. So we get these distributions over possibilities, and instead of committing to one. So that's sort of the magic that allows us to get a lot of the non-determinism of our models, just to say that the non-determinism is being encapsulated in the vectors that are encoding observed structures. They're not sure about what they're looking at, but they're representing all the possibilities. So that's my next item here. So non-determinism, or what are called belief states in like reinforcement learning. Oops. Non-determinism or belief states corresponds to essentially non-determinism or beliefs in human processing. So maybe this is what distinguishes interpretation from prediction. There might be some kind of categorical perception where when you look at a prefix of a sentence, you're pretty sure you know what's going on because you're argmaxing over all the predictions that you might make, but you're ready to go to a different, you're ready to resurrect a different option if the new word comes along and is compatible with something that wasn't the argmax. So maybe the difference between interpretation and prediction is prediction psychologically is prediction is the things that you know are still uncertain, and interpretation is the part where you are unaware of the other possibilities until some context brings them out. And so the way that we can, there's lots of algorithms for dealing with non-determinism. So one is you just, right? So you compile it out, as we were just seeing, where like the embedding of a prefix is giving you some distribution over all the things that you might see. But there are lots of other algorithms for dealing with it as well, like dynamic programming algorithms, or beam search, or particle filtering, or message passing. So this is sort of the algorithmic part of a traditional NLP class. So I could mention a few other things here. We have nested models, like bi-level optimization. And the reason we need that in NLP is pragmatics. I said already the reason we need recurrent models. Yep. Is compositionality. And the reason we need attention, sorry, I should mention this up here, is sometimes when we're building up those representations like a recurrent tree, we might want unbounded branching in that data structure. And attention is basically just a method for letting us look at a whole bag of objects, maybe augmented with positional embeddings, and pool over all of them in a relatively clean way. Okay, so what all this adds up to is kind of a mode of thought. It's a way of thinking about, like when I was an undergrad, we had to take core classes for breadth requirements. And so if you took one in history, they were trying to teach you how a historian's mode of thought, like how it is that you approach assessing evidence. And if we go at the problem of teaching an NLP class from sort of the computational linguistics mode of thought, what we want is to teach how to look at the problem of what it is that people do, so their performance is, or their competence is evidenced by their performance, and think about how we might be able to build models that do the same thing. And that just forces us to pull out lots of different kinds of machine learning topics, but they sort of emerge naturally by yanking on that goal. So I'm forge ahead here, and I see here that I was optimistic in thinking that there'd be lots of time for discussion. But I want to talk about some other ways that you might organize a class. And hopefully there will still be some time for discussion. All right, so the one that we just covered here was if you're doing computational linguistics, we start with something that's given, which is intuitions. So I'm assuming you're thinking now about how to teach to your first class or how to reorganize your class. So we've got some intuitions about language, and those are developed by introspection on synthetic examples and corpus examples. And what we want to figure out here is how do we formalize this as some problem which is safe for computer science. You know, language is squishy and it's mostly taken for granted by our students in the they take moral reasoning or social reasoning for granted, or their own aesthetic reactions, or their psychology as consumers. And we can say, look, you can actually study this stuff. People are behaving in a way which is sort of predictable. So if you want to, what's incidental here is they end up getting some formal linguistics. But officially what we're teaching them is, and they end up getting formal grammars. So they learn about the phenomena, maybe I should say here, phenomena of language, which is linguistics, and formal grammars, which is CS, and optimization objectives like maximum likelihood, which is statistics, and algorithms, which is CS. But that's not the way that you sell them on the course, right? You sell them by saying, we are trying to learn how to formalize what they're doing. So another way that you might do this, another way you might organize a course is historically. So you say what's given at every step, at every unit of this class is we have the state of the art as it was then. So the old state of the art, and what's to figure out is something to improve. And what you get here incidentally is like history of science. You get to see the paradigm shifts. That's kind of useful for, it empowers students as engineers to like step back and understand how it is that people have locked themselves into a local optimum and how they might unlock that. So all the times we've looked at the state of the field and said, this isn't quite right. One other reason that this is useful is that you do cover a lot of older stuff. And I don't know, it turns out that, I've been very interested since starting to spend some of my time in industry to see that a lot of these classical methods actually still get used. Like we are using the things where my PhD students say, oh, does anybody actually use that anymore? The undergrads are willing to trust me on this. The PhD students are like, isn't everything neural now? And it turns out that sometimes you want to put human knowledge into your systems. And so there is, still stuff like grammars and grammar engineering and dynamic programming algorithms because you want a human in a loop. So what does a historical picture look like? I could outline one, but let me save that as a question. I wrote out a whole outline of how I do this historically, and I'm not going to have time to do it. Okay, so the next thing that we might do is to focus first on phenomena. So here I put this as incidental, that the phenomena were incidental. But here, let's make the phenomena central. So we're given first a setting that natural language engineers happen to be interested in. So it's an engineering problem. And here's what you challenge the class to figure out. This is your mission as a class together, is how to set up the task to make it machine learning friendly. But now you're not trying to formalize it as competence or performance. You're trying to formalize as a task. And I could imagine here teaching a whole class around shared tasks. So you could do classical tasks like word sense disambiguation, NER, parsing, machine translation, information extraction, AMR parsing, morphological inflection, summarization. You could also do computational linguistics tasks like unsupervised discovery. There's a recent shared task on syntactic realization, turning a bag of content words into a sentence in each language, predicting human performance like garden path effects and reaction time. You can take tasks based around dialogues, multi-turn information retrieval or multi-turn question answering. So these are interactive tasks. Or we could take tasks which are basically like language in the world. So how do we mine lots of text to understand sociology, to be able to detect misinformation and harmful language? There's lots of goals that you could start out with here, different NLP settings. And a lot of this is how the community organizes its work. So the focus here is really the interface rather than the implementation. And the way that you teach this might actually be boxology, where you say you have these different units and they feed into one another and outcomes output. And what you get is sort of a incidental is some exposure to how the ML works and the state-of-the-art performance. So you get to know the numbers. So this is useful if you want to teach people in the same way, like in a compiler's class, kind of what's going in on the hood and what the thing is doing. Like if you wanted to use NLP, what NLP might be able to do for you, what are some of the tasks that it could actually work on. So I think for most NLP classes, where the data comes from is left vague. But here I think it's the machine learning that you would leave somewhat vague. And you spend a lot of, you open up the black box a little bit to say, here's roughly how the machine learning people solve these things. And you put these in an order maybe where you could sketch each ML system by extending or combining previous ML methods, but you don't break your head on over how those methods work internally. What you do break your head on is when you're formalizing this, how do you collect the data? What are the annotation schemes? What's the linguistic stuff that's going on that makes you have to worry about particular distinctions? And so what you get out of this is how do you, Dave Barry used to have, who is a humor columnist, used to have occasional columns called Ask Mr. Language Person. So, suppose you're working with machine learning folks and you are a mixed language person. So how are you going to work with those machine learning people? That means you need to know some linguistics. You have to be sensitive to linguistic phenomena. You have to know how to do data collection, exploring the data, through word clouds and every other kind of exploratory data analysis. You need to know how to do annotation, develop annotation schemes, evaluation metrics. You need to know how to do feature design and error analysis. And this is the kind of class you might teach, say, in a linguistics department, where the NLP settings are at the top. And when they're done, the students can go off and be in industry as the linguistics people. So in architecture, if you have an architecture-centric class, you're again going to start out with a NLP setting, as you have a series of NLP settings, but now you flip what you focus on. So what you take as the task, the crucial thing is how would I build the system? And what's incidental is, oh yeah, there's data collection and you have state-of-the-art numbers. It's just you're spending more time on one of these things than the other. But again, you're going through a series of settings, and when people are done, they need to know how to mix and match things every different way. Another perspective that you could do is this class really belongs squarely in computer science. So you are given a formal setting that linguists are interested in, not that engineers are interested in. Maybe, cross-serial dependencies in Swiss German or something like that. So you have like legal strings plus a scoring model. And now you need to figure out a grammar formalism. Maybe something funky like categorical grammars or LFGs or something, and algorithms for solving your standard problems like inference and computing the partition function and its gradient and so on. And what's incidental here is why the linguists care. So you're giving people some exposure to why your previous family of grammar formalisms wasn't good enough. And then the final way in which you might set things, and this is, I promise, the last thing I'll talk about, is, so I should just say that this makes actually a pretty nice advanced machine learning class, this one here, because when you come up with all these algorithms, you have to invent all this stuff in machine learning one thing at a time. You kind of basically reinvent all of the machine learning algorithms, but it's specifically applied to stuff like sequences and trees. I've kind of wanted to write a textbook for many years called like 13 Ways of Looking at a Hidden Markov Model, which says, there's a Wallace Stevens poem called 13 Ways of Looking at a Blackbird. And it's basically, every chapter would relate hidden Markov models to some particular kind of data and some particular kind of class of methods in computer science and machine learning. So finally, you could just start with some kind of moonshot goal. And that moonshot goal it could be something like, how do we search? There's lots of text out there. How do we give people relevant stuff? Or how do we communicate? It's a dialogue problem. How do people communicate? We want to build some agent. We're going to start with a really bad one, and it's going to get better and better over the course of the semester, and we're going to invent what we need along the way. Or there's lots of text out there. How do we do sociology? How do we understand how people are talking to each other? Part of the reason that NLP is hard to teach is that it's so expansive. We touch everything. We do not stay in our lane because language is like the #1 medium of human thought. It's how we think. It's how we exchange ideas. It's our vehicle of creative expression. It's our vehicle for most of our negotiation, for social jockeying. And because of that, you can just start with any area that you actually care about for its application reasons, and just like do NLP University. You could probably teach an entire undergraduate curriculum motivated just by one of these moonshots, where you're hitting all these NLP problems along the way, but also, along the way, you have to teach them some probability and statistics, and at some point you have to teach them linear algebra, you have to teach them calculus for backprop, you're going to teach them rhetorical structure theory, so they'll become better writers. Also, when you teach them linguistics, the corpus is going to consist of historical documents or documents about biology or about literature, and so you have to learn how to analyze those. So you can kind of hit any topic that you care about. I just think it's important to start out with something, with a mission for the class, where you always have something that's given and something that's the class's mission to figure out given that. Okay, so I am going to stop there, and we now have 1 minute for whatever questions I was not able to see during the whole talk. I'm sorry, I assembled a lot more material than I didn't even talk about all of it.
Well, thanks so much.
Okay.
This is a fantastic and thought-provoking talk. I love this formalism. We have a bunch of questions. We're happy to stick around, and thankfully we had a participatory activity after. So if you're able to stick around for questions, we're happy to take them now too. But
yeah, I'm very happy to. I don't want to distract from other activities in the workshop.
No, I think this actually leads quite well into the next discussion that we're going to have anyway on what kind of how to structure NLP courses. So maybe I'll start with one question from Drago. So he asked, we've been thinking about a framework for how to share teaching materials in NLP, because there are all these different approaches as you've kind of like enumerated. What do you think it needs to be? What do you think like such a repository or framework would need to look like for that initiative to be successful?
So that's not a question that relates directly to this talk. So I'm very happy to answer it during the discussion session. But maybe we could switch to one that has to do with the machine learning question, just to stay on topic a little bit, because I don't want to dominate the follow-up discussion on the question you just asked.
Sure. Let's see. Looking at all the other highly weighted. So I guess one of Yav's questions maybe was, do you actually believe that the embeddings can capture these like syntax nodes? If you want to ask that or refine that as well.
So it's about like can they catch? Like, do you actually believe the equivalent, or is it just like a nice metaphor for the class?
So here's one way of thinking about what's going on in like an RNN. After you've heard we talked about this in I think a 2018 paper in some detail, so I feel on pretty secure ground here. So you've got a bunch of words. You've got an HMN. So here's your hidden state after every step. And we know after you've heard 4 words, your brain is in some state. So you just remembered a bunch of things. The question is how you structured that. But you're in some state, and you're going to do an update when you see the next word, and that's called an observable operator, the thing that combines the old state with the new word to get your new state. And these observable operators in the case of an HMM are linear, but if you want to remember like everything from the first half of the sentence, then there's just an awful lot to remember. You have to remember all the outstanding stuff on the syntactic stack. You have to remember the topic. There's pragmatic stuff you have to worry about. You might be in the middle of a figure of speech, and so you need a tremendous number of a tremendously large state space to deal with this. So one way of thinking about what's happening when you train in RNN is that instead of doing linear updates in an HMM in a very large state space, you actually are mostly close to some manifold, low dimensional manifold in that state space. And so the vectors that are the hidden states in the HMM are basically coordinates with respect to the manifold. So now your updates are nonlinear updates. And so you're learning this kind of nonlinear dynamics. The question is whether that's able to simulate, whether that's successfully simulating all the stuff that you would be doing if you had, some really large factorial HMM. And I think we only know that by things like probing. I'm completely happy to build up structures that have latent variables.
Yeah, so I was asking actually about the lambda terms that you had there before, like the kind of more formal semantics, which seems to be like, at least to me, like about like a bit of a rough analogy, like between those and the embeddings. But maybe you.
Yeah, let me say a little bit more about that. So I have a picture up here that's back from my graphical models days, where I was explaining what a theory of everything might look like. There's plate notation here, where the stuff inside this box here is the stuff inside this box is tokens, and the stuff outside is types. So in other words, your knowledge of the language. And I guess I could have another plate because you might know many languages and want to do this stuff multilingually. So the reason that knowledge representation and reasoning is traditionally about logic is that logic was the universal solvent back in the 1960s and 70s when people started to do this stuff. So the idea was you had all these different modules of cognition, and that included language, but also facts that you might get from other sources, experts or sensory information or whatever. And all of these things had to be able to talk to each other. And if you could do reasoning, if you could do inference meant logical inference. And so writing down propositions in first order logic was a way that all of these different sources of knowledge could talk to each other. Nowadays, I think that's crazy, because when we think about inference, we don't think about logical inference, we think about probabilistic inference. And so I think what we really want is something that's more like, message passing in a graphical model where we have, beliefs about different random variables. And when we're doing discourse and I'm trying to convince you of something, I'm trying to change your belief state about the world, that stuff that's outside the language, by telling you stuff about my belief state, maybe not just by giving you facts, but by telling you about, say, if I give you causal or counterfactual statements, I'm telling you stuff about my probability distribution over the world and how, it's marginal if you were to intervene in a particular way. So you could think about probabilistic inference as being the universal solvent, but you could also do what a lot of people are doing and do multitask learning over a graph, which is very much like the one that I'm drawing here, where you have all the same kinds of random variables that you had before, and they're talking to each other, but they're all represented by embeddings. And your old graphical model, you either augment the random variables or replace the random variables by these nodes that kind of represent distributions over random variables, and then do message passing in a graph neural network. So there's surely some loss when you do that. And I think one thing that when we put our machine learning hats on, one thing that we have to figure out is how we can get back and forth nicely between system 1 and system 2. In other words, how we can say we can do this fine-grained case-based reasoning when we need to, but we can also get quick reactions when we don't need, when coarse-grained reasoning is enough. And how do we decide when we want to do the fine-grained stuff? So I'm thinking about like anytime inference. I don't know if this answered your question well enough.
I think it's fine.
You might be asking, like whether we're able to get all the way up to human performance or human competence, or you might be asking whether the current systems are actually getting anywhere near that.
Yeah, it was mostly the second, but I also kind of really enjoyed your view on the theory of everything, so that's good.
Yeah, this is great. Jason, there was a request from John Hale. Is it possible for you to share all, like, whatever this is, the correspondence that you had between machine learning concepts and linguistic ideas is really fantastic. And I mean, the structure and the course outlay, like, I'm not sure what format this is in exactly, but it'd be it's really
it's on this whiteboard here.
Yeah, it's excellent food for thought.
I should write it up as a blog post. I would have to get a blog first. But yeah, I'm happy to post something about it. Maybe an email to the new teaching list would be a place to do it.
Actually, if you could just hold on the screen there, we could all screenshot it.
Yeah.
Too.
Yeah.
All right.
I see the book is now.
Yeah. I don't know. I'm going to make it really small, and then you can blow it up again after you screenshot it. That's the whole trick. Yeah, I'd wanted to get a little bit more into some of these, so I should probably write it up. And I'd said if you want to do a historical version here, I have more to say about like my own historical view of the field and why all the ideas currently in the field got there, like what people were dissatisfied with at the previous step.
Ted, I think you had a question on that. Do you want to follow up?
Sure. On the historical approach.
Yes.
Yes. I made a couple of comments that I would love to hear more about that, because this is a thing I have thought about but have been afraid to pursue. And so I would like you to give me some courage on a more historical approach.
Sure. So do you want to?
Your thoughts on how to organize a class like that, or how would you basically pursue that? What is the overall plan there?
Oh, okay, I'll give you the quick story here of how I would think about it. So you're giving me an excuse to talk from my notes here. So the first thing that happened was let's zoom in here again. So I'm at roughly the same type size. All right. So generative grammar formalized what it meant to be grammatical. So it produced a way to turn our intuitions into formal languages, but transformational grammar wasn't very computationally friendly. So because of computation, we needed better formalisms. So transformational grammar never really hit. There was some work by Sandaway Fang in the 90s, I guess, 80s and 90s. But people really coalesced around other formulas like categorical grammar, LFG, tag, and so forth, that encoded movement in the non-terminals. And then also, I guess we could mention dependency grammar. But these things didn't give any story about ambiguity. So we needed scores. But then we needed a way to learn the scores. So we needed data. And we started worrying about curating and collecting data. Now, at this point, there is kind of a model versus policy tension. So are we going to model generatively or discriminatively, basically? Within models, there's generative versus discriminative models, but these two things over here are like end-to-end for a particular task, and this thing over here is where you're trying to get like a full scientific theory, which might work across tasks. Okay, so so there's a lot of talk about that. And there was a whole period where everybody was like doing their homework in public. Oh, I want to learn SAMs. Oh, I want to learn nonparametric Bayes. So let's find something to apply that to and get it published so I get credit for having learned that. But a lot of that was just people learning things by applying them to different problems. So now it's in everybody's toolbox. Okay, so we all learned lots of machine learning techniques. A lot of them originally were so over here, we were, I just write this here as a parallel track. We wanted better scoring functions. And so that let us larger model classes that didn't support full dynamic programming. So we couldn't do exact inference, or we could do exact inference, but only on some problem. So they were able to take more features into account. And what I have in mind here is, I don't know, we have like structural SVMs and CRFs, if you want a probabilistic version of that. So these only give you like conditional scores or conditional distributions. They can't do everything, or just like free-form models with approximate inference. And then we need like beam search or various kinds of message passing or whatever. And so we still use beam search today in things like seek-to-seek models. So that was better scoring via features. And we designed features for a while. And then from that, I'd go to something where we weren't so good at designing features. So auto features. And that's what I was showing before with the adaptive basis functions in this picture over here, where we started, we weren't so good at designing features, especially for two classes, I would say. So one was for lexical semantics, because we didn't have a good typology of lexical features. And we usually just, backed off from a word to like all words with the same two-letter ending, or just all words, period. So we were really crappy at getting lexical semantics features, despite valiant efforts by people like James Kosiowski. And we were also really bad at doing semantic representations and dialogue state representations, except for the simplest cases of dialogue state representations. And so instead of trying to handcraft these things, we went to representation learning. And this is fairly recent. So now, instead of designing features, we got features. And now this becomes the universal solver. And now, once we had this, we started eliminating latent variables. So let's just say speed, compile at inference. And we just hope that the representations will learn, in effect, marginal posteriors. So we'll just learn ways by multiplying by a matrix and pass it through a nonlinearity and do that several times. And hopefully we get something that's close to the marginal posteriors. Those can be hard to learn, actually. So there are actual problems where, like the autoregressive factors are hard to learn. We had a talk a couple days ago here at NACL saying, maybe you don't always want to do it that way because it's no substitute for reasoning. There are uncomputable problems or NP hard problems that you might end up trying to learn when you could have just used a model that did case analysis. So then finally, the other thing I should mention here is not enough data. And so here we end up with multitasking. So I should say here end to end. So generative multitasking. So starting with word embeddings, which were just solving a little task and we used it for other tasks, and going up to things like GPT-3 and generating synthetic data. So generative multitasking is saying you've got lots of free data. We should just try to predict parts of the data from other parts, and then synthetic data to try to get the right kinds of inductive biases in cases where we don't have a lot of data. And that is, I think there's some future things that we could draw here, but that's sort of historically, sort of my picture of the history of the field. I'm sure I left out things that I'll kick myself about later. Zoom out here again. Ted, is that useful at all?
It is. It's terrific, and I think our field is so broad and so complicated now. If you just start right, sort of at the state of the art, I think it's incomprehensible to a student, like how these things just fell out of the sky. I mean, and so I find myself wanting to go back and explain, well, we got here because of this, because of that. So I think this is really helpful.
Yeah, it's incomprehensible in one way. There's another way that you could teach a class, and I wouldn't say this is a bad thing to do. In fact, I think this is basically what Chris Manning does in his widely viewed class, is to sort of tear everything up and start. So, week one is word embeddings, and you just take them for granted they exist. So there's like a standard way that we do things now with our erector sets or Lego kits, which is, you're going to build a neural net of some kind, and we just wrap things around it. We have various pieces of neural nets that talk to each other, but let's just start with one. And from data, in comes an input, and out comes an output, and then we measure some loss relative to output star, and maybe we wrap some search around this. So you're doing something like a bi-LSTM CRF or something, but you're using your or bi-LSTM PCFG or something, and you're using an MLP PCFG. But whatever it is you're using, whenever you have a function you don't know where to get it from, you just stick in a neural net in kind of a standard way using these recursive encodings that I was pointing to before. And so that's pretty easy, right? And if you want to have some more structure to the task, you say, oh, actually, I have another data set too. And so that's going to produce like red input to the net, or another neural net that shares representations in some way. And now these things need to be able to talk to each other somehow, but you end up with, they share layers or something, but you get a different output and a different loss function that you compare to a different gold output. And just snapping these things together is not a bad way to throw everything away and start from scratch. It's just, you need a more task-centric view, I think, if you do that. And at some point in your later lectures, and Chris does this, you may want to go back and say, like, what have we given up from the old days? So then you can do your history then if you want. So that's the architectures version.
This is fantastic. I wanted to ask one question. So from Adam, what do you do when you're for students who like struggle in the class, or who like like aren't able to quite get in there.
So yeah, so office hours, you know, because one thing that's probably useful is to make sure that people have the right preparation coming in. I sent out an email last week to all of the students who are in my class or waitlisted for it, saying, you know, the only actual prerequisite for this data structures, but we do say that you should have at least basic familiarity with partial derivatives, matrix multiplication, probabilities, and Python. And so if you're, and I should probably have added like big O analysis, but they get that in data structures. And so if you're not completely comfortable with these things, here's what we're going to do with them. And here are some places that you can look stuff up ahead of time so that you're not like trying to catch up. There are always going to be people who have trouble. One thing you can do is have people team up in the class. So most of my assignments, I allow people to work together under admonishments that everybody is supposed to contribute. It's not like you just sit there and you watch other people work. So I can, if you want, you can ask on the mailing list and I can share my admonishments. But if you have a group of 2 or 3 people working together, that can often help pull people along so that they still get something out of it, even if they didn't have quite the right background.
Great. I guess one more question from the thing. Actually, Ada, do you want to ask that? You'd written it, or I can ask for you. If you... Okay, so the question is, one can think of machine learning from a cognitively inspired or like anthropocentric perspective, but you don't have to do it that way. And
right.
Would you be doing the students a disservice by assuming that worldview of like a cognitively inspired machine learning?
So, I think it's important to admit that the models that we're building are wrong. Mm-hmm. But they're still useful in 2 ways, 3 ways. One is that they are at least a starting point for building better models of cognition. A second is that they are actually useful in getting results. So I tell the students when we do noisy channel machine translation, so I'm introducing the noisy channel thing about, I don't know, a quarter of the way through the class, maybe a third of the way through. And I tell them, you know, what this means is when you go to France, you are trying to understand all these people speaking French. And your theory is that they actually have English in their head, but they're trying to mess you up. It's coming out of their house, you know, they distort it as it goes from their brain to their mouth, and you're trying to reconstruct what they were really thinking in English. So of course, this is a joke, right? Everybody knows it's a joke, but it's a joke with an implementation that actually works reasonably well, you know, so you can do the IBM models. So the first thing is, you know, you didn't get all the way, but at least there's some engineering impact, even though it's the wrong scientific theory. And the third reason that you might teach the wrong tool is it's still a useful tool. It's a useful tool for learning, and it's a useful tool because in some other cases, it may be the best thing that you have. So I think it's fine, Ada, as long as you acknowledge what you're doing. It's the usual discomfort in engineering. You know, and engineering is, nobody knows why, nobody knew for a long time why aspirin worked. But you're trying to match the herbs that you have with the ailments that your patients have.
That's a great analogy.
Medicine is engineering, biology is science.
So are any other questions from the audience? Thank you so much, Jason, for sticking around too. If you do have questions, feel free to just raise your hand and ask them, or unmute.
We could just go into the, I'm really grateful that you've given me, in effect, an extra half hour in the talk. But, you know, we might want to go to more general discussion. And I know there was a question that you had before about sharing course materials from Drago.
Yeah, so yeah, we had some long discussion Well, we're thinking again about how to share all these materials between us, given that there's such a diversity. I think in the interest of time, I know we have lots of folks on the, well, at least a few folks still joining us from Europe. We may wrap up a bit early, organized